A car is being driven along a straight road. The diagrams A, B and C show the horizontal forces acting on the different cars. So in the first one we've got 500 newtons going left and 500 newtons going right. So if they're in opposite directions we have 500 minus 500. We're going to subtract them because they're going in opposite directions. That means 0 newtons. So the motion will be a constant speed. Remember, 0 newtons resultant force means a constant speed. For this one, we've got 500, and we're going to minus 200, so we've got a 300 newton resultant force. That means it will accelerate, and it always accelerates in the direction of the resultant force, which is to the right. This one, we have 200, and we're going to subtract 500, so in this particular case, well, we should have done it the other way around, sorry, but I was just trying to show you some negative kind of force. So this is going to cause a 300 newton force that way, and that will cause the object to decelerate. Right, here is the first part of the overall stopping distance. So the whole thing is the stopping distance, and the stopping distance is made up of the thinking and braking distance. State one factor that changes both the first part and the second part. So remember from the theory video, this is the speed of the car. Speed is going to affect both the braking and the thinking distance. At the point of the collision, the car exerts a force of 5,000 newtons on the barrier. So if there's 5,000 newtons on the wall acting that way, then the barrier must also act with 5,000 newtons. This is Newton's third law. So for every action, there is an equal and opposite reaction. So that is 5,000 newtons. Remember, it is equal and opposite. Suggest why the dummy is fitted with electronic sensors. Well, that will be to record the forces acting on the dummy. Use the graph to calculate the acceleration of the car just before the collision. So we're looking for a straight line part, and we're looking for a point where it's easy to tell from the graph. So if we look at the graph, whereabouts is it easy? Well, at this point here, it's going to be easy to get a value, and at the top, it's going to be easy to get a value. So if we use those points, they are the easiest points to find values. So what's the difference in time? The difference in time is going to be 4 minus 3, which is equal to 1 second. What's the difference in velocity? Well, it's from this point here to this point here, so that is the end velocity, which is 10, and we're going to minus 6 away from that, which is 4. So if we do 4 divided by 1, that's going to give an acceleration of 4 meters per second squared. Remember, acceleration is in meters per second squared, and we're just dividing the change in velocity by the time it took for that change in velocity. Okay, so describe the upward motion of the shuttle 1 second after launch. Well, you can see that this force is greater than this force, so this means we have an overall resultant force, and that means we have acceleration. Any resultant force will cause acceleration in the direction of the resultant force. By the time it moves out of the Earth's atmosphere, the total weight of the space shuttle fuel tank and booster rockets has decreased, and so the air resistance. How does this change the motion? Well, if we've got a greater resultant force and an even smaller resistive force, we're going to have a greater acceleration. So the size of the resultant force is dependent on, the size of the acceleration is dependent on the size of the resultant force. The greater the resultant force, the greater the acceleration. Okay, write down the equation that links acceleration, change in velocity and time. So remember, acceleration A is equal to V minus U divided by T. Calculate in meters per second squared the average acceleration of the space shuttle during the first 9 minutes of flight. So we know from the previous question that it reaches its velocity of 8,100 meters per second, and that takes 9 minutes. So if A is equal to V minus U over T, then we know that it's reached 8,100 minus 0 that it started at, and it's taken 9 minutes. Now 9 minutes is 9 times 60 seconds, and 9 times 60 is equal to 540. So if we divide that by 540, 8,100 divided by 540 is going to give you an average acceleration of 15 meters per second squared. Okay, the next question says, how is the velocity of an object different from the speed of an object? Well, velocity is a vector and speed is a scalar. Scalars only have a magnitude, which is just a number, and vectors have a magnitude and a direction, so they have both. Right, so the next question is about a crane using to lift a steel girder. So you've got this steel girder which has got a mass of 200 kilograms and it's being lifted up to the top of a 25-meter building. The girder accelerates from rest to a speed of 0.6 meters per second in the first 3 seconds, and then it rises at a steady speed. So we're calculating the acceleration of the girder. So again, A is equal to V minus U over T. You need to learn that. We know that the end velocity is 0.6, and we're going to subtract that from the start velocity, which was 0. Remember, V is the end velocity, U is the start velocity. How long did it take for that acceleration? 3 seconds. So 0.6 divided by 3 will give you 0.2 meters per second squared. The next question asks you, what is the weight of the girder? Well, weight is equal to mass times gravity. We know the mass over here is 200 kilograms. And we're going to multiply that by G, which we'll say is 10. So that will give you 2,000 newtons. Okay, the next question asks you to calculate the power of the crane motor as it lifts the girder at a steady speed of 0.6 meters per second. Right, so we need to get the power, which is equal to energy divided by time. Now this is one of those questions where you have to link different parts together. So we need to work out the energy, and the energy is going to be equal to the work done. Now how do we work out the work done? Well, we've got a force here, and energy, which is work done, is equal to force times the distance. Okay, so we need to know that the distance moved is 0.6 meters. Now how are we going to work this out? Well, we know that this is going 0.6 meters per second. So in 1 second, it's gone 0.6 meters. So work done is equal to force times distance. We know that the distance moved is going to be equal to 0.6 meters, and that's times by the force or weight, which is 2,000. 2,000 times 0.6 is going to give us our work done, and that is equal to 1,200 joules. Okay, so at 0.6 meters per second, if I just try and explain that a little bit better, speed is equal to distance divided by time. So if our speed is 0.6 and that is equal to our distance divided by our time, then distance is equal to speed times time, and the speed is 0.6, and we multiply by the time taken, which would be 1 second. So to go 0.6 meters per second in 1 second would give us a distance of 0.6 meters, and that's where I've got my 0.6 meters from. Now I've got my 1,200 joules. I know that power is equal to energy divided by time, so I'm going to use the same time, which was 1 second. So power is equal to my energy, which is 1,200, divided by my time, which is 1, and that gives you 1,200 watts. Right, a new motor is fitted to the crane. This motor accelerates the girder at 0.3 meters per second squared. Calculate the force which the crane applies to the girder to produce this acceleration. So we're after the resultant force which gives the acceleration. Now resultant force is equal to the mass multiplied by the acceleration, but we need to know the overall force. So this is a bit of a tricky question because they're asking for more than one thing. Now, the first thing is we need to work out the combined forces of both. So we know that the downward force is 2,000 newtons. That is its weight. So we've got a weight of 2,000 newtons. So in order for the girder to be on the crane, we just draw that little crane. This is my crane, by the way. In order for this to travel at a constant speed, the upward force would have to be 2,000 newtons. So just for it to travel at a constant speed at 0 meters per second meters per second squared acceleration, then we would need an upward force of 2,000 newtons. But we know it's accelerating. So for a constant speed, you need 2,000 newtons. So we're going to use that in a second. We've got 2,000 newtons just for it to have a constant speed. For it to accelerate, we also need the mass times by the acceleration. Okay, so we're going to take 200, which is its mass from over here, and we're going to multiply that by the acceleration, which is 0.3, and that will give us a resultant force of 600 newtons. So to really calculate the acceleration, you need to know the force that enables it to just be balanced at a constant speed and the force that gives it an acceleration. Both of those combined is the force that applies the acceleration. So 2,000 plus 600 is 2,600 newtons. So the answer is 2,600 newtons. And the reason for that is because you need to add the mass times the acceleration to the force that just keeps it balanced at a constant speed. So that's a bit of a difficult question. I think if you put 2,000 newtons, you may get 1 mark. If you put 200 times 0.3, you may get 1 mark. If you put both of those combined together to 2,600 newtons, you would get full marks, and that's how you get that answer. Right, a person takes their dog for a walk. The graph shows how the distance from their home changes with time. So, which part of the graph, A, B, C, or D, shows them walking the fastest? Well, this is the steepest part of the graph, which is B. This is the steepest gradient. So, the steepest gradient. During the walk, both the speed and the velocity of the person and the dog change. How is velocity different from speed? Well, I've just talked about this. Velocity is a vector and speed is a scalar. So look back at the video just on the last slide and you can see what those things mean. Right, the next one, draw one line from each velocity time graph to the correct statement. So we know this is a constant velocity, and if we have a constant velocity, it moves at a constant speed. They mean the same thing. And when you change the velocity, a change in velocity here means that you get acceleration. And this is a constant acceleration because it's a straight line. Use the correct word from the box to complete the sentence. The velocity of an object includes both the something of the object and the direction. So that is the speed. At the start of a race, a horse accelerates from 0 to 9 meters per second in 4 seconds. Calculate the acceleration. Well, again, that equation is A equals V minus U divided by T. The initial velocity is 0, which is U, and the end velocity is 9. 9 minus 0 divided by the time taken, which was 4, is going to give us 2.25 meters per second squared. When the horse accelerates, what, if anything, happens to the air resistance acting on the horse? Well, anything that speeds up is going to create more air resistance, so that is going to be greater. Okay, so in the next question it says a horse and a pony walk across a field at the same constant speed. The horse has 4,000 joules of kinetic energy. The pony is half the mass of the horse. What is the kinetic energy of the pony? Well, the kinetic energy has to be half. Why is that? Because Ke is equal to half times mass times velocity squared. So if we half the mass, if this goes down by half, then this one has to go down by half because they are proportional to each other. Okay, if you tried out some numbers, you'd be able to work that out. Okay, so if you're not certain why, just use some numbers for 2,000 joules and you'll be able to see the reason for that. Right, a car has a leak. Every 5 seconds an oil drop falls from the bottom of the car onto the road. What causes this? This is going to be gravity. The diagram shows the spacing of the oil drops left on the road during part of a journey. Describe the motion of the car as it moves from A to B. Well, if the car was going at a constant speed, it'd drop, and then it'd drop, and then it'd drop, and you can see that these spacings would be the same because every 5 seconds it's going to drop it the same distance away. Here, the distance is getting greater. Well, if the distance is getting greater, but the time taken is still 5 seconds here, and 5 seconds there, and 5 seconds there, you can see the distance travelled for each 5 seconds is greater. So what must be happening? It must be accelerating. And why is that? It's because the drop spacing increases, so the distance travelled per drop increases in the same amount of time. So drop spacing increases, so the distance travelled per drop increases in the same time. That's important. It's taking 5 seconds every time. So the time hasn't changed, but the distance of the spacings has. Okay, the size of the braking force affects the braking distance of the car. State one other factor that affects the braking distance of the car. Well, that could be the speed. A braking force of 3 kilonewtons. Remember, kilo means 1,000 times bigger, so it's 3,000 newtons is used to slow down and stop the car in a distance of 25 meters. Well, we're going to use work done is equal to force times distance here. What is our force? 3,000 newtons, and we're timesing that by 25, and that will give us our work done. Okay, so 3,000 multiplied by 25. So 3,000 times 25 is equal to 75,000, and that is in joules, remember. Right, the next question. The arrow represents the force of the water produced by the engine propeller. This force causes the boat to move. So why is that happening? Well, when it spins, it's putting a force on the water. So if the propeller puts a force on the water, for every action, there is an equal and opposite reaction. So what must the water do? The water must apply an equal force. They must be the same size. So explain why. As propeller spins, a force is applied to the water. The water then applies an equal and opposite force on the propeller or the boat. I'm going to write boat because it's less letters. Okay, and this moves the boat forwards. Right, the boat accelerates at a constant rate in a straight line. We've got from 4 to 16, so A again is equal to V minus U divided by T. Our end velocity is 16, our start velocity is 4, it takes 8 seconds. 16 minus 4 is 12 over 8, which is equal to 1.5 meters per second squared. Okay, the skier has a mass of 68 kilograms. Calculate the resultant force acting on the water skier. So RF is equal to mass times acceleration. We know our acceleration is 1.5, we've just worked that out. The mass is 68, so 68 times by 1.5 is going to give you 102 newtons. Right, the force from the boat pulling the skier forwards will be something compared to answer B part 2. So will it actually be this force? Well, no it won't, because to actually move them forwards you will have some air resistance and some friction in the water, which is drag. So that means it must be greater than, and the reason for that is because there is drag which needs to be overcome. Okay? Right, what type of energy does the car have at X? Well, that's gravitational potential energy. What type of energy does the car have at Y? It's going to be moving, so that gravitational and potential energy store. So we've got this store of GPE, and that is going to be transferred to our kinetic energy store. So that's going to be kinetic energy. Remember, kinetic energy is movement energy. Right, the graph shows how the velocity of the car changes with time between y and z. Which feature of the graph represents the negative acceleration between y and z? Remember, this is the gradient. So the gradient represents the acceleration, or in this case, the deceleration, which is negative acceleration. Which feature of the graph represents the distance travelled between y and z? Well, if we knew the values, this area in a velocity time graph represents the distance, so it is the area. Okay, the next question, there's a lot of information about a particular practical. It says calculate the average velocity in centimeters per second between R and S for trolleys. Write your answers in the table. Okay, so velocity, we're just going to use speed is equal to distance divided by time. So the distance is 65, and we're going to divide that by 2.1, and that will give us 30.95, and the other one is going to be equal to 80, and we're going to divide that by 2.6, and that is going to be equal to 30.78. Okay, it says in the question that it's worth 3 marks, so we need to think about why that might be. Well, this is quite simple. So what we're going to look at in the table is how many significant figures have they quoted the values to. Well, this is 2 significant figures, and this is 2 significant figures, so we're going to give our answers to the same as what we've already been given in the table. So make sure you give your results to 2 significant figures. This to 2 significant figures, we're going to have to round to 31. This to 2 significant figures is also 31. So the answer is 31 and 31. We are quoting our answer, our mean, in the same value as what is already in the table. Right, the next question, it says student 1 predicted that the trolleys would travel the same distance. Student 2 predicted that the average velocity of the 2 trolleys would be the same, and student 3 predicted that the negative acceleration of the 2 trolleys would be the same. Is each prediction correct? Justify your answers. Okay, so student 1, are they correct? Well, no, because D is different. So D is different, so they are incorrect. Student 2, they are correct. Why are they correct? Because the velocity is the same. And number 3, they are also incorrect because the time is different, so they are incorrect. Time is different. Okay, and if the time is different and the velocity is the same, And if we just go back to what it asks you, the acceleration has to be different. Okay, because remember, acceleration is the change in velocity divided by the time. So if they've got the same velocity but the time's different, then their acceleration has to be different. Right, what causes force A? Well, that is friction. So force A is friction between the tyres and the road. What causes force B? That is drag, or more specifically, air resistance. Right, this next question was on the theory section, the theory video that I put on it, and it was about terminal velocity. Okay, so I'm just going to quickly explain this, but you can use the mark scheme to see exactly what points that you need to include. Right, between points X and Y, we've clearly got a change in velocity here. So the biggest change is here, and then it's increasing to that point, and it's still increasing, and then it levels off. So between X and Y, we must have a resultant force. A resultant force causes acceleration, and that is a change in velocity. Okay, so we've got a resultant force and an acceleration, and that causes a change in velocity. When we get to Y, there is a larger resistance, and this is air resistance, so we're going to call that drag. So we've got a larger resistance or drag. The force acting is the same. So imagine it was a falling object. In this case it's a cyclist, but we've got the force of the pedaling cyclist pushing forward, and drag has increased. So between X and Y, the first point, we've just got this forward force pushing forward. We've got very little resistance, and that creates a much bigger resultant force and therefore a great acceleration. When we get to Y, we've still got this same forward force, but the resistive forces have increased, and therefore the acceleration is less. Eventually we're going to get this flat part, so it's asking us what happens between Y and Z. Well, eventually we're going to have the same forces. When the force is the same, there is no resultant force, and if there is no resultant force, there is no acceleration. Okay, if there's no acceleration, it is a constant speed. So if you could put all that into good written communication, you're going to get 6 marks. So you need to use these key points. You always talk about resultant forces. When there is one, you get acceleration. When there's a smaller resultant force because of drag, you get less acceleration. And when there's no resultant force, you get no acceleration and a constant speed. Okay, so on the next question, it asks us, the cyclist used the brakes to slow down and stop the bicycle. A constant braking force of 140 newtons stopped the bicycle in a distance of 24 meters. So work done is equal to force times distance. Our force is 140. We times that by 24, and that will give us 3,360 joules. Remember, it's the energy transferred, so it's in joules. Okay, when the brakes are used, the bicycle slows down. The kinetic energy of the bicycle will decrease. At the same time, the thermal energy, or the temperature of the brakes, will increase. Right, so the next part is all the answers. So if you just want to look at the mark scheme, then I'll leave these on for a couple of seconds and you can pause it to see the mark scheme.